Welcome back, everyone. So we have the last session of this week, and we have Piotr Przytycki, who will tell us more about the bioautomaticity of Coxeter groups.
Can everybody hear me? So since this is the last talk of the first week, and some of us are not going to be here, let's thank Radhika and Suraj for organizing this great conference. So let's do a recap of what we have been doing so far. We constructed a particular language for the Coxeter group, and here is the construction. For any element G of the Coxeter group, we look at the closest walls to G, which was denoted as curly W of G, and we look at the set of geodesics from identity to G, and we intersect the vertices on these geodesics with what's on the left of curly W. We call this curly P. And our first theorem that we will prove today is that the set P of G has a largest element, which we call small p of G. So there is an element that's larger than any other element in this set. Second theorem will be that the distance between this P of G, this voracious projection of G, from G in the Cayley graph X is bounded by a constant only dependent on the group. And once we have this voracious projection, given element G, we look at its projection, the projection of the projection, etc. We look at all the geodesics from G to identity that go through these points, and we put in the language the labels of all the geodesics from G to identity that go through these consecutive projections. So that's the definition of the language. And today, we proved part of fellow traveler property, part 1. Today we'll prove part 2. We'll prove these theorems and we'll justify why this language is regular. Any questions before we start? Okay, so let's get to work. Let's do fellow traveler property part 2. And for that, we will need one theorem that is difficult to prove. So this will be sort of a black box to us, but hopefully you will see it's intuitive. It's called the parallel wall theorem. This was proved by Brink and Howlett and was conceived earlier by Davis and Shapiro. So here is what this says. Start with any Coxeter group. So let G be any Coxeter group. Then there is a constant D that only depends on the group, such that for each wall W and each element G in the group at a distance larger than D from W in the Cayley graph, so we have G, and we have the wall W that's far from G, at distance greater than D. There is another wall. There is another wall in the Cayley graph separating G from W. So if G is too far from W, there is another wall in between separating G from W. So that's the parallel wall theorem, and that proof is rather difficult and I have to omit it, but you can look at the paper of Brink and Howlett for the proof. While I have this theorem on the board, I would like to record the corollary. So let me define a particular set of walls called elementary walls. Let epsilon be the set of walls not separated from the identity in the Cayley graph by any other wall. So all the walls closest to identity. And by the parallel wall theorem, we have the corollary saying that these walls are at bounded distance from identity, so that this set epsilon is finite. Questions? And now we are ready for the second part of fellow traveler property. So let's state it as a lemma. I will just write fellow traveler property part 2. This is the content of the lemma. No, with this definition, the script W of identity is empty because there are no walls separating identity from identity. So remember, with fellow traveler property 2, I have identity. I have some element W. Say, let me draw it for the moment somewhere here, and I have that equality that W bar is supposed to be equal to S W bar prime. And we are supposed to show that if W and W prime are in the language, then these two words, W and SW prime, fellow travel. So denote maybe as for the first part of the fellow traveler property, denote by G W bar and by G prime W bar prime. So here, in fact, I have my element G, and there I have two paths from identity to G. I have the path labeled by W, and I have a neighbor S of identity, and then I have another path labeled by W prime from S to G, and I need to show that this path and this path fellow travel. So that's the statement of fellow traveler property 2. And we assume that both W and W prime belong to the language. So we need to appeal to the definition to see what's the difference between these paths. And let's first see what this picture on the left can tell us to the picture on the right. So first of all, let's look at this bottom path. When I go from G to identity, I am bound to go through the voracious projection of G. And let's see what do we know about the other path. So remember, G is equal to S G prime by this equality. So this path, W prime, labeled by W prime, again, since W prime is the language, has to go through the vertex that's S times P of G prime. Because if we just multiply by S on the left, remove all those S's, I need to have path in our language. So if we start from G prime and at the identity, I have to go through P of G prime. So might be a difference between these two paths. Here we are bound to go through P of G, and here we are bound to go through S times P of G prime. And it might be that for some time, these two vertices are equal. It might be that even though we project this G towards identity on one hand and towards S on the other, these projections are still the same and there is no difference in the paths drawn on the left. So let's assume that we are at the moment where there is a difference. So while there is no difference, these definitions coincide. And the claim is that we can assume to look at the place where these two paths, starting from G, going towards S and identity, where they split, where these projections are different. So we can assume that the projection of G is different from S times the projection of G prime. Questions? And we'll try to see what happens with this configuration. So what does it mean that these projections? Yep.
So if they were equal, would you be using the constant distance property?
If they are equal, I just replace g by p of g and look at the next stop on our path.
No, but you still have to figure out the section from p of g to...
Yeah, but again, this w prime is labeled by, remember, w1 prime and w2 prime. This w is labeled by w1 and w2. And indeed, these two words are short. So if these paths are at the same point, they can be at most a distance c, one from another. So, but let's assume that these points are different. And what does it mean? So how do we define these points? We define them using these red walls. And there are not so many walls in which G, the configuration between G and identity differs from the configuration between G and S. The only wall that separates G from identity that does not separate G from S is this wall that splits the edge joining identity to S. So if there is a difference between these projections, this red wall needs to come into play. And this red wall needs to appear as one of the walls closest to G. So this means if these projections are distinct, that the only wall by which identity and S differ, this wall is just WS. This means that WS belongs to the one of the closest walls to G, separating G from identity. And since it's the closest wall to G, the projection of G has to lie beyond this wall. So I was correct to draw this projection on this side. On the other hand, since this wall does not separate G from S, this projection stays on this side because we are following a geodesic, and a geodesic cannot cross a wall twice. So we have this situation that these projections land on two sides of the wall separating identity from S. Okay, so now let's try to understand a bit more this situation. So as we said, these two paths labeled by W2 and W2 prime are short. They are a distance at most, of length at most c, where c is the constant from theorem 2. So this means that the distance between SPG prime from the red wall is at most, this is at most 2 times c, because this is c, this is even smaller than c, so this is at most c. So now we do the following trick. We reflect this point in the red wall. The reflection in the red wall is multiplication on the left by S, so the reflection of this point in the red wall is just the point P of G prime. And since this point was a distance at most 2c from the wall, well, this point is also a distance at most 2c from the wall. So all in all, when we look at P of G prime and P of G, they differ at most by 6c. So note that the distance in the Cayley graph between P of G prime and P of G in X is at most 6c. So that's good. They are bounded distance. And so now if we look at the path in our system, so if, which is labeled by an element of our language from P of G prime towards identity, we know that these paths fellow travel. Because if they were distance 1, they would k fellow travel. If they are a distance at most 6c, they 6c times k fellow travel. So these two paths stay close. Maybe, let me write it here, that thus the words W, the 1 and W1 prime, this path is labeled by W1. This path, since it's the reflection of this one, is also labeled by W1 prime, W1 and W1 prime, 6 C times K fellow travel. But we want to prove that the right path and the left path fellow travel. For the moment, we know that the right path and the middle path fellow travel. So what remains is to prove that the middle path and the left path fellow travel. Any questions before we justify that? Mm-hmm. Because otherwise there will be no difference between those two projections. This wall had to be one of the closest walls to G in order to make a difference. I mean, this wall wouldn't be in this set if it would not separate G from identity. And this K on the right is the constant from the first part of the fellow traveler property. So it's good that we did it in this order. Once we have the first part of fellow traveler property, we have our constant K from that part, and we can plug it in here. Okay, so as I said, it remains to prove that the middle path, which is the middle word, which is labeled by W1 prime, and the left word, which is labeled by S W1 prime, fellow travel. We don't know yet what will be the constant. So fellow travel, and we'll see in a moment what will be the constant. Let me keep the statements of these theorems. Okay, so how to prove that these two paths fellow travel? One is obtained from the other by the reflection in the red wall. So if we could prove that one and the other path stay close to the wall, and at the beginning they are close, at this point they are 2C close to the wall. If we could prove that they stay close, then we would have what we want. So this will follow once we justify that these two paths, so the elements on one path are just the prefixes of SW1 interpreted in the group, and the elements of the other path are just prefixes of W1. It's W1 prime. Prefixes of W1 prime interpreted in the group. And let me erase the parallel wall theorem because you have a figure on the right. So we need to prove that they stay at uniform distance from the wall WS, independent of anything, just the group. So what happens if they are not? What happens if they happen to be at some point in distance larger than D from the wall? If they happen to be, if some point here happens to be a distance larger than D from the red wall, then we use parallel wall theorem. There is a wall separating this point from the wall. So in particular, this wall has to cross that path somewhere. This is too short, so it has to cross here. And it cannot cross a geodesic twice. So it has to cross this path somewhere here. And this contradicts the assumption that the original red wall was in WG, because we found another wall that's closer to G. Let me write all that. So otherwise, if it's too far, if it's not at uniform distance from WS, then by the parallel wall theorem, there is a wall separating some point of this form from the wall WS. Some point S W1 prime of T from WS. And this, as you see in the figure, contradicts the assumption that WS was in one of the walls closest to G, separating it from the identity. So this ends the proof of part 2 of fellow traveler property. Yeah, you can stare for a while, because this picture is more complicated than the last one, and see if you have any questions. So you can now see how these theorems 1 and 2 combine to get both parts of fellow traveler property. And now let me justify why theorems 1 and 2 are true. So I will need another small black box, which if we had more time, maybe I could even justify for the affine case, so you can doodle and try to prove it at least for the affine case. So this is a property of Coxeter groups that was christened as bipodality by Dyer and Holweg. So they proved this in 2016. We were with Damian unaware of it, and we proved it in our paper, but they were first. So here's the theorem. So suppose you have an element G, and suppose in the Coxeter group, and suppose that it's separated from the identity by two walls, WS and WT, where S and T are generators. So let G be separated from the identity by the walls WS and WT with distinct S and T in a generating set. So the picture is you have identity, you have G, and then you have the wall WS and the wall WT separating identity from G. These are generators, so these walls are distance a half from identity, very close to identity. And suppose G is separated from one of these two walls, say from WS, by another wall. So if G is separated from one of those walls, WS, but equivalently you could require WT, by another wall, then G will be separated also from other walls going through this point. So we can take the reflection in T and the reflection in S, and these two reflections generate a dihedral group, and we can translate, using elements in this dihedral group generated by these two reflections, we can translate these walls to get some other walls. And the point of bipodality is that these walls will be also separated from G. So then G is separated from any wall that I just described in the red color, from any wall that's obtained by translating Ws by an element of this dihedral group St, or maybe by translating Wt by an element of this dihedral group St by another wall. Rotating or reflecting. So action by the group acts by left multiplication, by I call all these elements translations. Yes, in this example, these will be rotations or reflections. Yeah, but they are not parallel because they both separate identity from G, and they are both at the distance half from identity, so they have to intersect. So the theorem says that G is separated also from any of these red walls by some other wall. Maybe there is one wall for one red wall, and maybe there is another wall for another red wall. But not only G is separated from Ws, but it's separated from any of these other red walls by some wall. What's that? If it's separated from Ws or from Wt by a wall, then it's separated from any of the red walls by another one. Yes. So I have to except possibly for Wt. Thank you. Okay, so let's see how this is useful to prove theorem 1. And in fact, I will deduce theorem 1 from a similar theorem that we later, using the same proof as with Damian, we proved this theorem with Yikayao, and independently it was also proved by Dyer, Fischl, Holweg, and Mark. Similar theorem with similar proof. So we look at, again, at the Coxeter group, at the identity, and we look at all elementary walls. We look at all walls closest to identity. So let me draw this example that I am drawing all the time. With octagons. Let's see where are the elementary walls, the walls that are closest to identity. Well, this one, this one, this one, this one. Okay, there will be quite a lot of them. Two more. This one, and this one. Okay, so this is an example of those elementary walls, the walls closest to identity. And the theorem, I'm supposed to take a component of the complement in the Keeling graph. So let Q be a component of X minus the elementary walls. Then the theorem states that Q has a smallest element. Q0, the set of vertices of Q has a smallest element. You can observe that this is true in this example. So for example, this component has this as the smallest element. This component has this as the smallest element. Well, there are some components that just have one element. This one has two elements. This one is smallest, etc. For each component, there is this particular smallest element of the component. So I'll now prove this theorem using bipodality. Any questions about the statement? Yes. So in each component, there is an element such that for any other element of that component, there is a geodesic path starting at the other element, ending at identity, and going through the smallest element. What's that? Well, if it's smallest, it's unique, because if you have two smallest elements, one would have to be equal to the other. Okay, so now proof of theorem. So here is the method. So we have this component Q. We have, and the danger is that there are two elements that don't have a lower bound. So there we might have some element, say Q0, inside the vertex set of Q0 of Q, some Qn, and the danger is that there will be no lower bound. So we will prove otherwise. We will prove that for any Q0 and any Qn, there is some element Q which is smaller than Q0 and smaller than Qn. Since this set, and this will prove that there exists a smallest element, since every element has only a finite number of elements smaller than it. Okay, so it suffices to show that for each Q0, Qn inside the vertex set of my component, there is Q inside the vertex set Q0 with Q0 greater or equal than Q, smaller or equal than Qn. Then we will prove that there is a smallest element. Okay, so let's be naive to start with. Let's just connect these two, Q0 and Qn, by a geodesic. This geodesic will be contained in Q because we just cut our original space using walls. So the complementary components are convex in the sense that if you take geodesic between 2 points or one component, they have to stay in this component. But with respect to the distance from identity, this geodesic might do weird things. It might be that it first goes up, then down, and then down, up and down, and up and down. So if this geodesic behaves like this, there is no good candidate for Q. And what we will do, we will try to push vertices of this geodesic towards the identity, even at the cost of this path ceasing to be a geodesic. We want to push this path so that it has the following form: Q0 and smaller vertex, smaller, larger, larger, Qn. And if we'll know that here the distance from identity decreases and here increases, then we will know that this is a good vertex bounding from below both Q0 and Qn. So we consider a geodesic, call this first geodesic pi. So pi starts with Q0, then it has Q1, etc. Qn. And we will modify this path pi so that eventually, after some operations, there is no local maximum in the interior. So we want to eliminate situations like that. If we eliminate situations that we increase and decrease, we will have to be in this situation, so that there is no triple of consecutive vertices such that the first one is smaller than the second one, and the second one is larger than the third one. If we eliminate these local maxima, then our path will look like that. So this will allow to take for our lower bound Q this particular Qi, maybe some Qj, to take Q equal to some Qj. Okay, so this is a strategy. And now I need to tell you how to eliminate those mountains here. Okay, so what happens if we have this bad configuration? What happens if we have Qi minus 1 smaller than Qi larger than Qi plus 1? So what happens if we have Qi minus 1, Qi plus 1, and identity is somewhere here? Then we look at the walls that cross these two edges at the midpoint. So we look at this wall, call it WR. Look at this wall, call it W, maybe R prime. These are some reflections. And now we are very close to the situation described in the bipodality, except that this vertex is not called identity, but Qi. But in order to do it, we just can multiply this whole configuration by Qi inverse. So in this situation, we will consider the whole set of vertices that's obtained by reflecting Qi in using the group generated by these two reflections. So we consider this set R, which is obtained from Qi by translating it by the group generated by R and R prime. Okay, so let's say for simplicity that they intersect at angle 60. So if you start reflecting, there will be one more wall associated to this dihedral group, and here you will have a hexagon. Okay. You have some dihedral, this is some dihedral group. Let's say for simplicity for this figure that this is a dihedral group of order 6. And our job is to try to replace this path inside pi with the complementary path, because this will remove this mountain from our original path. We want to replace this mountain with this longer path, but whose vertices are closer to identity. But in order to replace this blue path by this bottom path, we need to make sure that the vertices of the bottom path belong to Q. So this is the main claim where we will use bipodality. So the claim is that R is the set of these extra vertices that I've just drawn, that this R belongs to the vertex set of Q. Okay, so let's prove the claim by contradiction. So what would happen? What does it mean that some of these vertices do not belong to Q? Remember, Q is a component of the complement of these elementary walls. So if we change the component by going along this path, this means that one of those walls is elementary. But we know that the original two walls weren't elementary because the blue path stayed in the component Q. So the original two walls weren't elementary. So this means that the extra wall in this dihedral group was elementary. So now proof of claim. Otherwise, this wall, call this wall just maybe W, this wall W belongs to the elementary walls, the walls closest to identity. Now we apply bipodality. So exactly in the way I mentioned, just by mapping this picture, in this picture Qi to identity, so applying bipodality with G equal to Qi inverse, what do we get? The conclusion of bipodality told us that the red wall is not an elementary wall with respect to this point, that there is a wall separating it from this vertex. So conclusion of bipodality fails in our situation, because in our situation, this one is an elementary wall. So if the conclusion of bipodality fails, the assumption must fail. So if the assumption fails, this means that this wall Ws and also Wt have to be elementary. So we obtain, say that Wr is an elementary wall, but this contradicts the fact that here we didn't change the component, we stayed in Q. So or here we didn't change the component, we stayed in Q. So we assumed at the beginning that Wr is not an elementary wall. So this is a contradiction, and this proves the claim. Okay, so bipodality is suited to be able to prove that you can replace this path in Q by this complementary longer path, which turns out also to be in Q, and this way you can remove those mountains and eventually get into the configuration I just described. So let me maybe write here the final sentence of the proof, that once we have proved the claim, we can finish the proof of the theorem. We now replace in the path pi the blue path, the path Qi minus 1, Qi plus 1 by the complementary path in the hexagon. By the other path with vertices in R, and then we proceed inductively. So proceeding inductively, removing these mountains one by one, we obtain a path that doesn't have those pathologies, a path with no situations that Qi minus 1 is smaller than Qi is larger than Qi plus 1. And as we discussed, this allows us to say that this is the behavior of our path with respect to identity, and this Qj is then the lower bound for the endpoints. So this proves the theorem. Questions? Comments? So in this theorem, we produce the smallest element of the component Q, and let me justify now how this produces here the largest element of P. So let's deduce theorem 1 from theorem 2. So now we will prove theorem 1. And this, so originally with Damian, we proved this theorem 1 directly using the same proof, but the fact that actually you can deduce theorem from theorem 1 was suggested to us by Holvik and Parkinson. This implication from theorem to theorem 1. So I don't have any more the definition of P on the board, so let me draw it again. We had identity, G. We had those closest walls, curly W of G to G. We had the geodesics. And P of G was this set cut out by the geodesics on the left. We need to prove that this P of G contains an largest element. So take this picture and multiply it on the left by G inverse. This is times. Multiply this picture by G inverse, then instead of identity, I will get G inverse. Instead of G, I will get identity. These walls now will become elementary, but it will not be all elementary walls. There are some elementary walls that are not obtained from translating these ones. Yep.
So you said R is a dihedral group.
These are the vertices obtained from Qi by acting on it by this dihedral group. No, because again, these two walls are closest, are a distance a half from Qi, they separated from identity. So they cannot be parallel. If they were parallel, then you would have this kind of picture, and identity would lie on the left wall and on the right of the right wall. So this cannot happen. Okay, so let me write what I just said, that if we act by G inverse on this set W of G, then it's contained in the set of elementary walls. But there might be some other elementary walls in E. It's just that they don't appear here because they don't separate G from identity. There might be just walls that when we translate back, they are positioned like this. Okay, but now we look at component Q containing G inverse and we apply theorem 1. This theorem tells us that there is a minimal element, call it a smallest element, but still call it M, in this component. So let Q be the component of the complement of the elementary walls containing G inverse. And maybe note that the set we are really interested in is this curly P of G. So let's see what happens when we translate it. So this set was, first of all, is on the correct side, it's on the same side of all these walls in WG as identity. And also, since these other elementary walls don't separate, when we translate back, don't separate it from G to identity, we know that this entire set is mapped to a single component Q. So now that when we act now on P of G, this is contained in Q. So our set whose here maximum we are looking for is contained in the set whose minimum smallest element we know. So now let's justify that this, once we translate, actually we contain M. So let's introduce this notation. So let M be the smallest element in Q, the smallest in Q, exists from theorem 1. And then in particular, since M is smallest in the component Q containing G inverse, in particular, G inverse is larger than M. Because M is smallest than any other element there, so in particular, it's smaller than G inverse. And so, this means that M belongs to G inverse curly P of G. Because the condition on being in curly P of G was you had to lie on the right side of those red walls in WG, which we have. Q is on the correct side. And you have to lie on a geodesic from identity to G. But since Q inverse is larger than M, well, by definition, this is a geodesic. So by definition of P of G, M is contained in the translate of P of G. And thus, if we translate back, then if we translate M back by G, this is largest in P of G. Since M was smallest there, G of M is largest here. So this ends the proof of theorem 1. And remember, we can record from this construction exactly how to construct this voracious projection. In this case, the voracious projection is obtained by taking this particular M coming from theorem 1 and translating it by G. So this finishes the proof of theorem 1. So the real difficulty was in the theorem, and then there was a relatively easy carrying over of this statement to theorem 1. Questions? Well, the G inverse, so group elements act on the left on the vertices of the Cayley graph. So G inverse act on the vertices by multiplying on the left. And what is a wall? Wall is a set of midpoints of edges. But if you have an edge of the Cayley graph, by acting on the left, it's also transported by another edge of the Cayley graph. So the midpoint is translated to another midpoint, and that's how we act on walls. So all the top, so it's a continuous action on the Cayley graph, even isometric action on the Cayley graph. So all the notion of connected components, etc., are preserved. More questions? Okay, and now I can justify theorem 2. Our original proof with Damian used cut-zero geometry, but now you will be able just to use the parallel wall theorem or its corollary. So this was also suggested to us by Holbeck and Parkinson. So proof of theorem 2, and this particular proof is by Holbeck and Parkinson. So we use corollary to parallel wall theorem. It's erased already, so I'll just write it again. So by corollary to parallel wall theorem, the set of elementary walls is finite. So we have this finite set of walls cutting the Cayley graph into components, but since there are finitely many walls, and it's easy to see that there are only finitely many complementary components. So thus, the number of components, since they are convex, of the complement is finite. At most 2 to the number of walls. Hence, there is a constant that only depends on the Coxeter group, such that since there are finitely many number of components, there are finite number of smallest elements in all these components. Remember, for each component, the theorem provided the smallest element M of each component, and there are finitely many of them. There is a number C such that each smallest element M of a component Q, as a minute ago, each smallest element of a component Q of the Cayley graph minus the set of elementary walls satisfies that the distance between this element and identity in the Cayley graph is smaller than C. It's just that there are finitely many elements. We take them C to be the maximum distance of the set of these elements from the identity. And this gives us the right bound C, because our job is to bound the distance between the voracious projection of G to G in the Cayley graph. But we constructed a moment ago the voracious projection as the translate of M. And G was the translate of identity. So for the moment, it's just P of G is equal to G of M. And now, multiplying by G inverse on the left, this is just the distance between M and identity in the Cayley graph. So this is smaller than C. So this proves theorem 2. So at this moment, up to the proof of parallel wall theorem and up to proof of the bipodality, you have a complete proof of fellow traveler property. And what remains is to prove that the language is regular. Questions? Comments? Doubts? Mm-hmm. So we need to look at the definition of P of G. So in order to prove that M belongs to G inverse of P of G, we need to prove that G of M belongs to P of G. So why G of M belongs to P of G? Being in P of G had two axioms. First of all, to be in P of G, you had to be on the geodesic from identity to G. So that's exactly what we have here. Since M is on this geodesic, G of M is on that geodesic. So that's one of the properties. And the second property was that you needed to lie on the appropriate side of these walls, but this is guaranteed by the definition of Q. Okay, to prove that a language is regular, I need to produce an automaton. So now I will write down the automaton. Okay, let's state it as a lemma that the language L we used all the time is regular. I write down the automaton. Probably we won't have time to look at all the details, but then there will be something for you to think about on the weekend. So here is the proof. Remember what was an automaton? There was a graph, directed graph. It had to have labels from either the empty word epsilon or the alphabet. And here we will allow for slightly more complicated labels. We will allow to label edges not just by letters, but the entire words. But it's easy to turn, if I now tell you to label an edge by a word, you can turn it into the original automaton just by drawing a long path labeled by each consecutive edge just by one letter of this word. So here I'll be labeling the edges of the automaton by entire words and not just by letters. And I'm supposed to pick the start state and the end state. Okay, so we first define the vertex set. We will say what will constitute the vertices of this automaton. The vertex set we denoted it as gamma 0 on Tuesday. So the vertices will be the power set of the elementary walls. As the power set, so the set of all subsets, all the subsets, maybe I will not use this notation because P stood for something else, the power set of E. So all set of all subsets of the set of elementary walls. It's a finite set because, again, we had a corollary from parallel wall theorem that this set of elementary walls is finite, so the set of subsets is also finite. And the start state will be the empty set. Accept states will be all the states. And now I need to define the edges. It will be a bit mysterious for the first 5 minutes, but then hopefully I'll be able to convince you that this is the right choice. Okay, so now to define the edges from a state, gamma. Okay, remember a state is something weird, it's a set of walls. Let me draw it here. So I have my identity vertex, I have my set of elementary walls, but I don't take all of them. I just take some of them, maybe the empty set, like at the start, and call this set gamma. So gamma is a subset of the set of elementary walls. And now, what edges do I draw from this? So this is called the vertex. This is called the vertex of our automaton. And what edges issue from this vertex? So to define these edges, suppose that you have an element H in the group satisfying the following properties. First of all, we want H to lie in the same component of the complement of these walls, red walls, as identity. So first axiom, H is not separated from the identity by any wall in the set gamma. So if we are at the start state, this condition is empty because there are no walls in gamma. Part B, H is separated from each wall in gamma by another wall. Okay, so it's relatively far from identity because for each of those red walls, I want to have at least one wall separating H from this wall. So from this, similarly from this wall, we would like H to be separated. So H is relatively far from identity according to this axiom B. And axiom C says that actually H is relatively close. Maybe if you take the voracious projection of H, it's equal to identity. So it's not too far, because remember, voracious projection jumps at most by the constant C, so H is not too far. And if we have these properties of an element H, we draw the following edge in the automaton. Then we put an edge, or maybe even several edges, between gamma and we put an edge between the configuration of red walls and the configuration of blue walls, but translated by H inverse, so that this point is moved to identity. So these blue walls, probably you notice that this is exactly or a subset of WH. So we look at WH and we put an edge between gamma and H inverse translate of WH, and the labels are all the shortest words, representing H. Okay, so this might be a bit mysterious, but let me say a few words why this automaton will do the job, why. So the claim is that L is the language of this automaton. L is the language of this automaton gamma. And in fact, the main thing to prove, so the claim is being proved inductively, but you need to, inductively on the length of words in the language, but the main thing to carry over through the induction is the following, that the accept state, we know a bit more about the relation between this language and the paths it labels in the Curie graph, namely the accept state of each such word in W, in L, is exactly the set of closest walls to G translated by G inverse. And this is the thing that you need to prove inductively. Maybe let me draw a final figure. So the automaton needs to produce all those arbitrarily long paths that satisfy the property that we are going from identity to G, going through those voracious projections. This is P of P of P of G. And the states the automaton will go through are exactly the following states. The automaton needs to produce a path which labels any such path. And the way this path will appear as a path in the automaton is that we will start from the empty state, from the state where the set of walls is empty. Then, if you look at the definition of an edge, you will see that taking for H this element, since identity is the projection, it's not hard to prove that the next, we are allowed to jump to this state, which is, so we go from this empty state to the state H inverse W of H in the automaton. And then there is something to prove, namely that we are allowed to jump to the state which is obtained by translating this P of G to the identity and translating simultaneously these words W of P of G to identity. So we need to prove that then in the automaton we can go to P of G inverse W of P of G, etc. So this is how we progress in the automaton. There are these states, each of which corresponds to a configuration of these walls separating consecutive vertices from the identity, but where we translate these vertices here. And you need to prove inductively that if you start with a word in the language, then it labels such a path, and conversely, if we have a word labeling such a path, then actually it can be produced by the automaton. So I leave it as an exercise, and this ends the proof of biautomaticity. Thank you.
Any questions for Piotr?
So for example, let's see, what the basic is the A2 tilde. Okay, so you're asking what the automaton is or what the language is? Yeah, so what the paths are, it's, let me. Well, see the power set, there were 6 elementary walls, to the power 6 is a lot. You can still remove some of the configurations because there are some connected components of the automaton. So some of them are redundant. So maybe we could do it, but I don't have it prepared, so I will not attempt to do it in my minus 5 minutes. But for the question about the to see the path system here in the plane. So say, for example, we go maybe from this vertex to this vertex. So remember the voracious projection needs to go, say, through this wall and through that wall. So it will jump first here. This will be my first voracious projection. I can go either this way along the hexagon or this way. Once I'm here, my walls separating this vertex from this one, W of this point, are now 3. So I need to jump here, and then I just jump by 1. So I go either along this path or this path, then I go either along this path or this path, and then I do this. So in fact, in this example, these will be all geodesics between. Although no, not all, because this one, you're saying it's not a geodesic. Okay, yeah. So that's what happens when I try to improvise. So let's see what were the walls separating this vertex from the identity. This one is the closest. This one. Identity was here. Okay, so this is the so this is the largest element. So this is the voracious projection. And then actually I'm in a similar situation where this wall and this wall separate. So I jump here and then I jump here. So yeah, okay, I shouldn't expect more because here in this example the geodesic was unique. But in order to conceive some better example, maybe we should go okay, let me draw this grid again. Probably something interesting will show up if I will go from this vertex to this one. Because there is a geodesic from this vertex to this vertex going like this. Because the Cayley graph is the dual to this one. So there is a geodesic doing this. But this is not in the language, because in the language I am supposed to jump here, and here, and then here. So there are 4 paths in the language going from this to this, because these are consecutive voracious. Or maybe, let me see. What is the voracious projection of this one? No, the voracious projection of this one is immediately that. But still, we don't go, if you take the path going through this voracious projection and then through this, none of these paths going through this point can pass through this or that. So you see that we don't get all the geodesics between these 2 points. We get only the geodesics going through these voracious projections. So it's like this bed that we are allowed to follow. Mm-hmm.
But then it ends at that G itself might not be erased.
Yeah, but we go from this here. This is obtained as voracious projection of this. This is obtained as the voracious projection of this. So we go this way, But then we have to prove that this vertex is obtained as the successor of this vertex in the automaton. So we have to work our way backwards when we prove this lemma.
I was just thinking that the endpoint of that path there, G, if G is, I don't know. The way it's defined, it seems like the states of the automaton correspond to Parish's projection.
The states of the automaton correspond to possible configurations of a, yeah, the states just correspond to a situation where you take arbitrary vertex, look at WG, and translate this WG by G inverse. These are basically the states. And you have to prove that that when you produce this path in the language, in our language L, then actually this path is a path that appears in the automaton we just built. That we jump from this state corresponding to P of G to the state corresponding to G, etc. Maybe 25 minutes exercise. You can do it. I can show it to you in the break, or you can do it with Davian on Monday if you decide it's a good plan.
Any other questions? So if not, let's thank Piotr again for the wonderful lecture.